Right. Okay, ready? Eyes down. So I'm just going to go through lenses and ray diagrams. So it used to be the case that you had to draw ray diagrams and do like scale drawings, like what you do in mechanics, where you add vectors and you do scales and you work it out, measure the tractor and things. You used to have to do that with ray diagrams, but they removed it from the syllabus. You still need to know how the rays go through a lens, and actually it's really helpful to understand the ray diagram for a telescope. So you could easily be asked to draw the ray diagram for a telescope, the one we're going to do tomorrow or Thursday. And I think it's helpful to understand why I've drawn those rays, because you're more likely to remember it, rather than saying learn that, which is one way of doing it. Well, I just want to go through how lenses work in inverted commas. What does a lens do to the light then? When light hits a piece of glass, what does it do? It diffracts. Everyone's happy with that? Refracts. Which one is it, Gabe? Refracts. Yes, it refracts. What does that actually mean if you're sort of telling it to a younger sibling who often will ask you what happens in physics? What did you learn today? We learned about lenses. What do? They refract. What does that mean, oh big and glorious brother or sister? And you say, well, obvious, it's... All I heard was a general mutter. So the best way of doing this is to put your hand up, and then I can see who wants to answer. Or if there's no hands, I'll just pick on someone. But Jamie's killed himself to answer.
Well, yeah, it bends.
It bends. Yeah. So the light changes direction. Why does it change direction? What is it about the glass block that makes it change direction? Jamie, again, you're on fire.
The refractive index, isn't it?
The refractive index in it.
It's different.
It's different.
Yeah.
Was that an explanation? If I'm a little brother or sister, does that make any sense to me? What is the refractive index? Is he? He'd know that, would he?
No.
You're on the right. I mean, it's a yes, but no, but yeah. So what is it? What is the refractive index telling you about material?
Well, the density of the
density. Yeah, the density of the air, the glass, and if the density is different, it'll change direction. Yeah? Is that right? Everyone's happy with that? Again, rabbit, people, a few little heads going up and down. It's not the density. Yeah, I was hoping someone would say density, and you very gratefully provided the answer I was after. It's not the density. The density doesn't lead to a change in direction. It's the change in speed which leads to change in direction. The change in density produces a change in speed, but it's the speed that makes it change direction, not the density per se. See, important, subtle, but it's the speed that makes the difference. So when things speed up or slow down, when they go from one material to another, then they'll change direction. So here we've got a light ray going in to this little dotted line here, which I refer to as the... No, this is all great stuff for revision, by the way. It's all good stuff for revision for paper 1. The naughty normal at 90 degrees. In physics, anything that's at 90 degrees is normal. Anything that's not 90 degrees, obviously abnormal. So normal stuff, 90 degrees. Angle of incidence, is it that one? Or this one? It is, of course... Which one's it going to be? B. See the clever little Darren Brown stuff going on there? That's the angle of incidence. So, glass, air, glass. So is this light ray with the whiteboards going to bend away or towards the normal? I perhaps shouldn't do this because all the students who had me last year, who I taught last year, had the most amazing acronym so they could remember which way it bends. So there'll be a distinct advantage. Unless you've forgotten the acronym, of course, in which case you're knackered. So is it bending away or towards the normal? I'll tell you in a second, and then you'll remember. Now look, there's the acronym. Very good. Hey, I mean, I don't want to keep going on about it, but this is much better than the previous class. Just saying, yeah? It was about half and half with the other class. They clearly had the Scoobies what's going on, but you lot are very good. Why does it change direction again? Because it's changing speed. So that's the acronym, FAST. Remember now, James? Yeah. So if the light goes faster, it bends away from the normal. If it's going slower, it bends towards the normal. How cool is that? Light bends because it changes speed. Acronym is FAST. Faster away, slower. I wish I thought of that. I wish I thought of it. Anyway, it's going slower in the glass block, so it's going to bend towards the normal. And then when it comes out the other side, it's going faster in the air, and so it bends away from the normal. And in fact, because these two faces are parallel, that light ray is parallel to that one. If I'd shone the light ray along the normal, it would, of course, go straight through. So actually, it wouldn't really change direction at all. It would just go straight through the glass block. Okay, well, that's fine. So light refracts when it changes speed, e.g. going from, I haven't said what it means, is it? Light refracts, i.e. changes direction when it changes speed, e.g. going from air into glass. I'm not going to bother writing the acronym down because you have it already in your notes from last year. But if you don't, you might want to sketch it down now. Now then, if you have a lens, the only difference really between a lens and that glass block I showed you before was the lens has curved surfaces. Don't copy this down. So you have a curved surface. So when the light ray comes in and is incident on the surface, remember we have to draw a normal, bends towards the normal, so it will go like that. Then we have another normal, and it'll bend away from the normal, like that. So the light ray ends up doing that. And because of the curvature of the surface, we can make it so that all of the light rays will pass through the same point there that we refer to as the focal point. That's really all the lenses are doing. And if you're a little spotty young boy, what you can do is take a lens like this, position on the ground a small ant or other invertebrate, and then put your lens there, and the sunlight from here will be collected and focused down onto the small invertebrate, and it'll burst into flames. I didn't do that, of course. I just burned paper, but other people might have used small insects. It's surprising when you concentrating just that much light energy and concentrating it down to a small point is enough to burn paper. Yeah, there's enough energy in sunlight to do that. All right. So lenses can be categorized as shown there. You can have lots of different combinations of surfaces, but these are the main two, like that, or like this. A bit further apart. Sorry. Sorry. Oh, it's a shocking drawing. It's so bad. Oh. That's better. Right. So this one is referred to as a convex lens, and this one is a concave lens. And the way to remember which one's which is that's like a cave because it goes in. Bit lame, but that's how I remember it. Yeah, so it's a cave because I'm going in, concave, and this is the other one, convex. Because of the way the curvature on both faces, then the focal points are at the same point either side. Each lens has 2 focal points. Now this is just to know. You won't be asked this again. It used to be that there was calculations on lenses. You can work out image and object distances based on the focal length. You can also work out what's called the power of a lens. The more powerful a lens, the more it's going to bend the light. Yeah? So more powerful lenses bend light. I mean, I should be saying refract light more, but you know, bend light more. This is really shocking English. Bend light more, so have smaller f focal length and are fatter lenses. Again, it's only relevant for telescopes because we have one lens which is very powerful with a very short focal length, and one lens which is very weak or not powerful with a very long focal length. And it's helpful to know which is which, that's all. That's why, yeah, the bigger the curvature, the more refraction you get. So this light is bent more, and so the focal point gets smaller. And vice versa if it's weaker. So thin lenses are weak, fat lenses are powerful. You don't need to do the calculation anymore, but power equals 1 over f in meters, and the units are dioptry or capital D. So anyone like me who's short-sighted, you might have -5 because I'm quite short-sighted, D, and that's the power of the lens that my eye needs to correct my shockingly bad vision. Okay, so that's the unit, it's 1 over the focal length of the lens. But you don't need to know that, and this is only helpful when we do the telescope, so I say the powerful one, the fat one, is here, and the thin one's there. That's why. Okay, so that's the general terminology. I'm going to go through the construction of the ray diagrams for lenses. It used to, I'll say it again, you used to have to do scale drawings and work stuff out. You don't have to do that now, but you still need to know what happens when you have objects at different distances from the lens. And in order to really understand the telescope ray diagram that you do need to reproduce, I think it's helpful to know what's going on. Okay? Can I rub that on? So here we go with a ray diagram. Principal axis, lens, convex, focal points, I'm going to mark them there, and the same distance there. So these two things here, there and there, focal points. There have been some really grim questions where you're asked to mark the focal points, a point of a lens, and people do that. And in fact, they lost a mark because they need to do that as well. So they weren't using this one. And we're going to put an object that we're looking at somewhere way over here, like that. Now, the normal convention is to represent objects as arrows, so you can see the position of the image that's formed, whether it's upside down or the same way up, and whether it's bigger or smaller. Okay, so the normal convention is to represent an object as an arrow. as you move the object further and further away from the lens, what happens is this image gets smaller and smaller and smaller and closer to the focal point. So you can see a lot of stuff here on a very small area there because of that. It's the same with a camera on a CCD. You know, the CCD's relatively small. How can you get a whole big picture in? Well, because the image that's formed by the lens of the camera is diminished, it's smaller, and so it all fits on the CCD. Yeah? Now then, you sort of need to know how to describe the image that's formed. I'm nearly finished writing stuff down now. I'll show you this first, actually. There we go. You see that? So here's the object, O. They've got 3 light rays in because they're doing it properly, unlike me, lazy, just do 2. And that's where the top of the image is formed, and so the image is there. And I can move this dynamically so you can see what happens to the image. Yeah, so I'll come back across here. I'm just going to put my pinky on top of that and then move it closer and closer and closer to the focal point. See what's happening? I'll move it further away. Look what's happening to the image. Then move it closer. So actually, when the object is exactly 2 focal lengths away, the image is formed exactly 2 focal lengths and is exactly the same size. When the object is between 1 and 2 focal lengths, the image gets really, really big. And it's the other way around to the object, but it gets bigger and bigger. And then it'll get bigger and bigger and bigger and bigger and bigger until eventually, if I put the object there, then the 2 rays from here and there are parallel. They won't cross anywhere, so you won't form an image. Okay? If I bring the object within 1 focal length, you get this happening. And the rays, if I do the ray diagram coming from there, like this, you can see these 2 rays are diverging. They're moving further apart. So they're not going to cross anywhere this side of the lens. However, if I was to look through the lens like this, then it would appear as if these 2 light rays were actually coming from this point here, up there. And so what you'd actually see is this object would appear really big, like that. Now this actually is simply a magnifying glass. Notice the action there. Anyone do drama? Look at the method acting. Magnifying glass. It's also a magnifying, the microscope works as well. But you can only see the image when you look through the lens, which is why with a magnifying glass, I can't get a magnifying glass to say, look, there's the thing, there's the little burnt ant, there's the magnifying glass, and then look everyone, I'm putting a screen up here, you can all see it. The only way to see the image is to look down the lens and form the image in your eye. Okay. So, a projector, not here anymore, but a projector would have the object between 1 and 2 focal lengths away, so you get a magnified image, yeah, upside down, which is why it's such a nightmare on the blooming acetates. And then if you've got a camera or your eye, then look at this. Oh yeah. If it's further and further away, this image gets smaller and smaller and smaller and smaller and smaller and moves towards the focal point. Nearly done. And there's 3 things, or 3 ways we describe images. Whether it is magnified, well, opposite of magnified is referred to as diminished, not smaller, diminished. We've got upright and inverted. And finally, real, man, or virtual. So in describing images, you'll pick one of these, each of these here. So it could be magnified upright real, magnified inverted real, magnified upright virtual, diminished upright inverted, whatever. Yeah, but you describe it as that and this, or that, or that, and that. One from each line. That's how you describe the images. So this one is the image magnified or diminished? Well, it's smaller, it's diminished. Upright or inverted? Now you have to be careful with this, because this actually means not is it the right way around or not. You know, if I had an object like that, and then the lens, the image would be like that. Well, is that upright or inverted? So what it means is it the same way around as the object or the other way around? So this one is the other way around, which means it's inverted. So actually, on the back of your retina, when you form the image is upside down. And your brain very cleverly flicks it around the right way. So everything looks the right way up. There was a very interesting experiment done where people wore glasses with mirrors on front of them, which flipped the image up the other way, if that makes sense. So to begin with, everything looked upside down. But after a while, the brain very cleverly flicked it round the right way again, so everything was upright. And then they took the glasses off and everything was upside down again, and the brain figured it out and put it back the right way. Yeah. Same with the camera. The image on the camera is upside down. Real and in virtual. Real means, this is the last thing we're writing, real means image can be viewed on screen. And so that just means the rays literally cross here. I could take a screen, put it there, and the image will be formed. Now I can't do that with a magnifying glass, because you can only form an image when you look through the magnifying glass. So the image of a magnifying glass would be magnified upright, it's the same way around as the object, and virtual. So for a magnifying glass, over here, so the magnifying glass, the image is the same way up as the object, upright, it's much bigger, magnified, and it's virtual, because I can't put a screen here and allow people to see it.